Hello, Sheldon.
Hello.
How are you doing?
Pretty good.
Thank you. There was one part of proof from last week to finish theorem on, I called it controlled finite interpolation. And there was a reason to call it controlled and finite, because when H is given as an RKHS on a set X, then F in H, is a function on X with values in C. Now, in reverse order, if a function is given, now F from X to C is given. And we were looking for some conditions such that this condition guarantees that F is in H. It's kind of important theorem with many applications. And the one we saw, the controlled finite interpolation. A part of it, I mean, part 2 indeed, which is, I mean, mostly used. Part C also used, in particular in the study of multiplier algebra, but also for the function f. But part 2 is kind of the heart of this theorem. I remind you about part 2. And we will see one more time why it is called controlled and finite interpolation. It says that there is a constant C such that for every finite set F, Xn in X, so that's the meaning of finite interpolation. There is a function X, there is a H in the space H, such that H at point xk is equal to f at point xk, k from 1 up to n. At n points, h coincides with f, and moreover, the norm is controlled, norm in H. So that's the meaning of controlled finite interpolation, two things. And it's to see the importance of this result, note that many functional spaces that we consider, the ambient space X, the space on which the functions are defined, is usually big. It's not even countable. For example, we saw RKHS on the open unit disk, RD space, Berkman space, Dirichlet space. So X over there is D. And the theorem says that choose any finite number of points. I mean, it can be, there is no restriction on Z1 up to Zn. And then if you can find a function h, usually we go for polynomials, but in this case, polynomials are not the best choice, because with polynomials, we can do this interpolation, but the other one, we are not sure. If you can find an interpolating function whose norm is bounded above, then the function you started with is in the space. So from something finite, you go to the whole space, not only separate. I mean, from finite, usually we go to a sequence, something separable, but here D is not even countable. So from a finite number of points on D, we go to the whole of D, and this is what helps us in application. We did 1 implies 3, 3 implies 2, and now it remains just 2. I mean, this possibility implies 1. In other words, why this implies there is a function which is in the space. And here is the point: instead of sequences, we use nets for our limiting process. So the assumption says that for any finite set f, there is a function h. So for any f, there is a function h, which I will denote it by hf, such that with this interpolation is possible and the norm is controlled by C. HF is not necessarily the best function in this space. I mean, the best in terms of the norm, which does the job. If we saw before in previous courses, if we project f to the space created by those kernel functions, the notation we used, it's h of f. So h of f is the span of kx, x in f. In other words, a span of kx1 to kx. If we project into this space, which is closed, being finite, we obtain a function which does the interpolation, and also its norm is smaller. So if I call g of f is the projection into h of f of this function hf, then gf at each point xk is equal to hf at each point xk, and this is, we know before, that is equal to f of xk, k from 1 up to n. And also we know, because of the projection, the norm of gf is less than or equal to the norm of hf, because we project it into a smaller space, and this is less than or equal to c. That is why we switch, and instead of using hf, we use gf. And now define M to be the supremum of all GF when F ranges over X and F finite. We know this supremum exists and is less than or equal to C. Now the claim is that this GF, so claim GF when F is a subset of X and finite is a Cauchy net. And we know that, I mean, there was a proposition at the beginning of this chapter. It's a Cauchy net which converges to F. So let's verify why is it a Cauchy net. I mean, at the beginning, we showed that the Cauchy net is convergent, but here it is easy to see that if it converges, there is no other option. It has to converge to F. But first of all, why is it a Cauchy net? By definition of supremum, given epsilon bigger than 0, there exists an F0 such that this quantity is close to M, I mean, as much as we wish, because it's a supremum, so we can get closer and closer to M. And for convenience, I choose F0 such that the norm of GF0, is it the squared here? No, it's not the squared. It's for sure is less than or equal to M, bigger than or equal to, we can put whatever we wish here, but strictly less than M. And I mean, the authors choose m minus epsilon squared. If you choose m minus epsilon, it's also true. I mean, we obtain at the end something which goes to 0, but epsilon squared is to obtain something a little bit easier at the end. It's not that essential. Now, what can we say if f is finite but bigger than f0, contains more points? Naively, I want to show that with capital F, the approximation is better. And to do this, put it here to see it better. Now, note that if I consider g of f, recall the definition of g of f. It's a function, it's here indeed. It's a function which is norm bounded, not bounded even by m, but I need this property here. It does the interpolation for all x in the finite space f, and f contains f0. So g of x, f of x, is equal to f of x for all x in f, in particular, for all x in f0, because it's smaller. And therefore, if I project this, therefore, when I project this gf into hf0, I obtain gf0. Remember, we had a theorem that when we project into the space created by kernel function, we obtain a function which does the interpolation, and also it is unique. So it doesn't matter with which function which does the interpolation you start. There are infinitely many of them. But when you project, you obtain the one which has the minimum norm. So P hf0 of gf is equal to g of f0. And therefore, because of the projection property, this implies that gf minus gf0 is orthogonal to gf0. That's because of this projection. And now you note that I can write gf equal to gf minus gf0 plus gf0, and therefore norm of gf squared is, by orthogonality, norm of gf minus gf0 squared plus norm of gf squared. And also note that norm of gf0 is less than or equal to the norm of gf because of the projection. So projection. And this is less than or equal to m. That's the definition of f, of m. And what was our choice of f0? This is bigger than or equal to m minus something, which we choose m minus epsilon squared. And now the effect of this is seen here. Here is the effect. Therefore, gf minus gf squared is norm of gf squared minus norm gf0 squared. A2 minus B2 is A minus B, A plus B. Less than or equal to. This one, I can replace it by 2 times the supremum. All of them is less than or equal to m. And this one, because of the inequality that you see here, because of this one, is less than or equal to epsilon squared. Therefore, GF minus GF0 is less than or equal to a constant times epsilon. For any f which contains f0. Now, if you can see the two f, let's say f1 and f2, such that both of them contain f0, then you repeat this inequality twice, and you easily see that GF1 minus GF2 is less than or equal to GF minus GF0 and GF1 minus GF0, GF2 minus GF0. And each of them is like big O of epsilon. So it gives us 2 times root 2m. It's a constant, C. It's not the same C that we had before, but well, it is CT times epsilon. And thus, this shows that GF, I mean, F is in X finite, is Cauchy. By proposition that we had at the very beginning of this chapter, there is a function G in H, better to mention here Cauchy in H, such that lim GF is equal to G. That by the first proposition. We know that convergence in norm imply the convergence in at each point-wise. Therefore, for any x in X, lim GF of X is equal to GX. But as soon as F contains the point X, if X is in F, then GF of X is finite, doesn't change. When I say finite, I mean with respect to our parameter, which is F. F is our variable here. And therefore, for any X in X, then G of X is equal to F of X. Conclusion, F is in H. This is what we wanted from the very beginning. It's kind of surprising theorem. And there is a very nice corollary here to show, on one hand, the mystery, on the other hand, the power of this theorem. And look at this corollary. Let F defined on D with values in C be a function. No other restriction for the time being. Be a function. Assume that this is the assumption we need to apply part 2. Assume that there is a constant C strictly bigger than 0, such that K of Z and W defined by this formula, C2 1 minus Z W bar minus Fz Fw bar is a kernel function. And it's better to say kernel function on D. Z and W vary sur D, on D. You see, it's in a sense, it's a question in linear algebra. What does this mean, kernel function? Means that can fix endpoint Z1 up to Zn, form the Grammy matrix K, Zi, Zj, and that is something positive. So let me mention here. This means that for any Z1 up to Zn in D, the matrix K, Zi, Zj is bigger than or equal to 0. So it's a verification in linear algebra. And now you see no mention of complex analysis techniques and all we have seen up to here. And now look at the conclusion. Then, conclusion. F is analytic on T. So from something in pure linear algebra, you conclude that a function is analytic, the derivative exists. And more than that, moreover, the sum n from 1 or 0 to infinity, I can call it an mod squared is finite, where an are Taylor coefficients of f. So we have two other unexpected results in complex analysis from an assumption in linear algebra. Just by verifying something is positive, you conclude that the function is analytic and its Taylor coefficient are square summable. It's quite, fantastic results. Really a surprise. And you can do this with all functions, with all RKHS that you have seen up to now.
I was just about to ask a question. Do they have similar results for the bidisk?
It's the
in this
theorem.
sense?
Absolutely, the theorem. Look, it's very general. There is. I didn't mention the whole statement of theorem here. It's on X. No restriction on X. X could here. I choose X to be D.
Mm-hmm.
You can take it to be D too. It works in any RKHS, and that's the real power of this theorem.
Okay, and that kernel would look the same. The only difference would be the functions.
The kernel here would be, instead of C2 over 1 minus ZW bar, it will be C or C2. That doesn't matter. But in denominator, you'll have 1 minus Z1 W1 bar times 1 minus Z2 W bar 2. It will be like that. And over there, FZ1, Z2, FW1, W2 bar. It will be like that.
Okay.
Okay.
Okay, thanks.
You're welcome. It works in any space.
Just want to note that it's not even obvious to me. I agree. This looks like a surprising result because it's not even obvious to me that the hypotheses implied that f is a continuous function on the basis.
Absolutely.
right?
Absolutely.
Not assuming that at all.
Yeah, positivity has proved to be a very strong tool. And in our focus program, there was a talk by Yura Lyubarsky. He talked a little bit about Gabor frames. And there is a recent work by Dominique Guillot. He also kind of marginally talked about it. Dominique Guillot and Apurva Kare and two more also, I mean, work on this, but a whole group of people on frame theory work on positivity. And the new notion that they have is total positivity, and they extract a lot of information after that. So at the first glance, as Sheldon mentioned, I mean, you just have positivity. You don't expect even the function to be continuous, but a lot more comes out of it. And here is one phenomenon that we witness. If you look at their work, they have a very nice recent survey about 70, 80 pages. They explain about total positivity. And you see, they just start from this. All the minors, I mean, the determinant of K by K, all of them, not just principal ones. If they are positive, they call it the total positive. And they extract many, many information from that. Okay, that finishes our chapter 4, and now we start chapter 3. Sorry, we start our chapter 4, which is indeed totally linear algebra. It's a lot of interesting stuff, but it's kind of, I can say abstract linear algebra, but it's better to say beautiful linear algebra. It's a lot of interesting stuff in this chapter. And it's mainly on Cholesky. And sure result. Sometimes instead of sure, we call it Hadamard, but we'll arrive at that. Let's start with Cholesky factorization. To do this, one observation. So, question. Assume that the 2 by 2 matrix whose first element is 0, and here we have B, C, D, is positive. So you have a matrix A, B, C, D, which is positive, but the first element is 0. A is equal to 0. What can you say about the other elements? It's not a difficult question, just we use the definition of being positivity, and we obtain the conclusion. And here is another point that what I emphasized before shows its importance. P being positive is equivalent to P of X and X inner product is bigger than or is 0 for all X in C2, not R2. I emphasized on this before, but its importance you'll see here. For any X in C2, the inner product of Px and X has to be positive. And now we choose, general X in C2 is of the form alpha and beta, where alpha, beta are in C. And then let's see what is Px inner product with X. It's not difficult to see that Px scalar X is, I write it here, it's alpha squared times 0, that's the first element, which is 0, plus beta alpha bar times B plus beta bar alpha times C plus beta squared in modulus times D. Well, it's very straightforward to see that B has to be C bar and D has to be positive, right? Special choice of alpha and beta. But more than that, I choose beta such that it's unimodular, and it's, in a sense, it's the argument of B. Beta times, is it beta or beta bar? Beta pki. So beta times B. Usually we choose this beta times B to be absolute value of B. But also we can choose it to be, if we add pi to the argument, we can choose beta such that beta times B is minus absolute value of B. And it will happen here too. I think okay. So what does this give to me? This gives, the first one is 0, and the second will give me minus alpha I choose to be in R to simplify. Really doesn't matter to be that complicated. Here I get 2 alpha absolute value of B, because in absolute value both of them are the same, and then beta is chosen such to remove the argument, and plus just D, this is bigger than or equal to 0. I divided, no, didn't do anything. This is just what I obtain if I choose alpha to be real and beta unimodular such that beta times B is minus mod B. It's a standard trick that we do when we want to prove the generalized Cauchy-Schwarz inequality too. This is not something very strange, it's standard technique. Why we do this? Because when you look at the last inequality here, you see immediately that alpha is free. So alpha can go to plus infinity. And if B is not equal to 0, then there is a problem here. The inequality will bigger than or equal to 0 will not be true. So since this is true for all alpha in R, immediately from this we obtain B equal to 0 and thus C also equal to 0 and D bigger than or equal to 0. Therefore, that's the end of. Therefore, if you have a matrix 0, B, C, D bigger than or equal to 0, then B is equal to C equal to 0 and D also bigger than or equal to 0. Of course, this is reversible, but I don't need that, but it's trivial. True. You can easily generalize this because the definition of positivity, so the lemma is here. If you have P equal to Pij n by n matrix is positive, and one element on the diagonal is 0, and Pkk is equal to 0. Then everything on the column of Pkk and on the row of Pkk has to be 0. Then Pik is equal to 0 for all I, and Pkj equal to 0 for all j. So if this is your P, which is bigger than or equal to 0, and on the diagonal, this element, say, is equal to 0, everything on this diagonal and on this row, on this column and on this row is equal to 0. And the proof is just we saw above. It is true that in the general case, when we write Px inner product with x, x is in Cn, but you can consider all the coordinate equal to 0 except 2 of them, the case 1 and another one, and then you obtain a 2 by 2 matrix and apply the previous result to that 2 by 2 matrix and deduce that everything here is 0, everything here is 0 too. True? So it's a nice observation, but it will help us to prove next theorem. Is it clear or? Okay. Theorem Cholesky. Let P equal to Pij n by n matrix be positive. And now we assume that the Pkk, the element on diagonal, is not 0. And it either say not equal to 0, but we know that it has to be bigger than or equal to 0. Therefore, this is equivalent to say that Pkk is strictly bigger than 0. It's the same. Then define the following matrix. There's no specific name for it, but the ij element of this is Pij minus Pik Pkj divided by Pkk by j from 1 up to n. I mean, call it Q. So we define a matrix Q like that, then Q is positive. The conclusion, the main observation is that Q is also positive. It is not clear why this is something important, but gradually we'll see, and even today we will see some application of this Cholesky observation, but there are more which will come in future. Well, before giving the proof, let's do some discussion or remarks. When we have two matrices A and B, and we do the product, there are several ways to look at this product. Usually, I mean, at the very beginning, we say that C which is the product of A and B, is a matrix such that the ij element is A, I, K, B, K, J when the summation is over K with appropriate parameters K from 1 up to depending on the dimension. That's the thing we do at the very beginning, which is good. We can prove a lot of stuff even with this original definition. But that's not the only way that we can look at the product of A and B. Let's provide some more, more insight, which is equivalent to what I mentioned here. Sometimes we need to do something about the columns of C. So we need to know what are the columns of C. So we look at C as a matrix of this form, column 1, column 2, and the last column. What are these columns? In these games, we do the same for B. So A times B, it would be A times the first column. I use C1 for column 1 and C2 for column 2. But these are the columns of B. And the result, the first column is AC1, the second is AC2, and the last one is ACN. That's one way to look at this product. Another way, still in this observation, when we say AC1, again, by the main definition, AC1 is a linear combination of the columns of A, which are gathered here. AC2 is another linear combination of the columns of A, which are gathered there, and so on up to the last one. If we are interested in the rows of C, then we need to consider the rows of matrix A. So here is R1, R2, Rm times B, and the product, it will be R1 times B as the first row, R2 times B second row, and Rm times B the last row. Again, R1B is a linear combination of the rows of B, which are gathered here. The same for R2B, and the last one is the same. So it's the second interpretation. And another one, which was kind of new for me, but it's very interesting, and we need it here. We look at A as a column matrix, C1 up to, say, Cn, and B as a row matrix. And note that it has to be Bn. So n columns and n row, and the product is precisely the product of C1 B1 plus C2 B2 plus Cn Bn. Note that R1, row 1, row n, sorry for that. Columns times row. So R1 up to Rn. And note that each time when you multiply Ci times Ri, you multiply a column by a row, and the result is a matrix. Usually, due to the scalar product, we do it in the other direction. We multiply a row by a column and we obtain a complex number. But here we need in the reverse order, C times R. Why did I mention this point of view? Because when we go back to the theorem, you might say, where does this come from? What is this? What is PIK, PKJ divided by PKK? Now, PKK is a constant, doesn't depend on I and J. We can take it out. But what would be PIK times PKJ? And here, it is immediate, observe that. The matrix, PIK, PKJ, PKK is just 1 over PKK. That's a constant we take out. And what remains is just V star, when V is the case column of the matrix B. Recall that PKJ is equal to PJK bar. So it's 1 over PKK, the case column. Here is P1K, P2K, PKK. Here, the last one is PNK times, when we do V star, either do star to this, so it will be P1K bar, P2K bar, but using this, you can say that is PK1, PK2, PK. So if you do this, you obtain the matrix you're looking for. There is another reason which I mentioned this. Up to here, it's all the linear algebra notation that we use. There is another notation that we use mostly in operator theory. So theory. If H is a Hilbert space, and X and Y are two elements of H, then X tensor Y is an operator on H defined by this simple formula. The action of X tensor Y on element Z is the inner product of Z and Y times X. So it's finite rank. Indeed, the rank is, if X is not 0 and Y is not 0, the rank is equal to 1, is usually one rank operator, 0 or 1 rank operator on H. So Z inner product with Y and then times X. So what is the connection between X tensor Y and VV star or CR as I defined here? Well, you have a column C, you have a row I, you multiply by them and you obtain a matrix, say n by n matrix. But this matrix, you can consider it as an operator on Cn. So we come back here. So if you have C and R, a column, a row, the whole thing here is an n by n matrix. And now what happens if this acts on a Z and Z is in Cn? Okay, I want to make a connection between CR acting on Z and X tensor Y to make it more clear. Note that for all vectors, we consider them as a column vector. So for X is true, is no problem. We can say that our C is equal to some X. But for our R, we should say it's Y transpose. Or, I mean, if you want to consider the conjugate 2, you can say that R is equal to Y star. There's no problem with that. And now, so X, Y star is well defined. What is the action of X, Y star on Z? Note that X is a vector like this, Y is a vector like this. So X, Y star is a matrix. And then that matrix acts on another matrix Z, which is still of this form. It's just a matter of calculation. There is nothing mysterious about it. Write the component of X, the component of Y, and the component of Z. Do all the products and simplify. And I mean, if you do the calculation, you see that this is nothing but the operator that we have in operator theory acting on Z. It's precisely the same thing. Okay, so we will see this in the proof of Cholesky theorem. Any question up to here? Okay, so let's have a break, and after the break we continue with the proof of Cholesky theorem.